Okay, this is a little video on, as part of the energy module, we need to look at something called thermal conductivity. What we're going to be talking about is we've got to think about different materials and whether they transfer heats at different rates. We're going to try and explain how the idea of conduction works using our knowledge of particles, and then we'll look briefly at a required practical. So first up, the basics. Conduction. Heat travels through solids by conduction. That's the overlying theme of this. We're talking about heat transfer through solids, and when heat passes through a solid, it is called conduction. Now, the best solids to do this are metals. Metals are very good conductors of heat, and generally, non-metals are quite poor conductors of heat. And if something is not a very good conductor, we would call it an insulator. Now, in the lesson at school, you may have done this practical, whereby you have different types of metal rod, and you use some Vaseline to stick a drawing pin, and you stick a drawing pin a set distance from the end of the metal rod. In my case here, it's 10 centimetres. You then, using a Bunsen burner, heat the end of the metal rod, and you time how long it takes for the heat to travel through the solid metal rod, and then as the heat does this, it melts the Vaseline and the pin drops off. So you test different types of metal and you record the time for the pin to fall off. These three dots are just showing you that you've got this clamped in a clamp stand for safety. Obviously this is going to get hot, so you don't want to hold it with your hand, you need to clamp it. Alright, so eventually you can just see on the animation there that the heat passes through and the drawing pin drops off, so you make a note of that time. Now, some of the results that you would be expected in the lesson, this is a bar chart to show the results. So we've got brass, copper and steel. Brass will have a time of about, or what's that, just over 80 seconds. Copper seems to be just over 20 seconds, and steel takes the longest, just over 140 seconds. So these type of results, what you now need to be able to do is to think about them in terms of the theme of the lesson, which is conduction, i.e. which material, in our case metals, which metal has got the best or is the better conductor. So we'll come through to that in a second, but just before we do that, a little bit of a side. Why do people get confused with the word conduction? Well, in physics you will meet two uses of the word conduction. There's thermal conductivity, which is how good something is at transferring heat, and electrical conductivity, which is how good it is at transferring electrical current or electrical energy. And in this table you'll see, you might know that silver seems to be the best conductor. Copper is probably the next best conductor, but in terms of thermal conductivity, we've got 428 for silver, which is very good, and then the next one is copper, which is 401, so that fits. Then shortly after that, 428, 401, we've got gold, which is 318. So you can see that these results do actually kind of fit and follow a pattern, but they are definitely two very different types of use of the word, and you just need to make sure you've got an understanding of both. Later on in the course you will talk about electrical conduction, but for today we're just talking about thermal conductivity. Okay, so back to our experiment. This is what was going on. If you imagine, if you heat the end of the metal rod, then here's the kind of Bunsen burner, and what you can see is on a particle level the particles begin to vibrate. As you add energy to the particles, they vibrate more, and as they start to vibrate, hopefully you saw on this little animation that the vibrations get passed along. If I just start it again, you'll see that nothing is vibrating yet. The particles on the end start to vibrate first, and as they vibrate they begin to pass the energy or the vibrations along the rod. In our case we've got a carbon rod, but it could be any other type of metal, and this is exactly how it works. Now the metals or the materials that are better conductors than others will have particles that vibrate more. So as you heat the metal, the particles vibrate. These vibrations make the adjacent particles vibrate. The adjacent means the ones next door, and so on and so on. The vibrations are passed along the metal, and so is the heat. Some metals are better at passing the energy on through these collisions, so they are better conductors of heat. So going back to our results, if I just skip back, it would appear our results, remember the shortest time was copper. So the shortest time is going to be the best conductor. That's key here. The longest time steel is the worst conductor because it took the longest for the heat to get through. The shortest time is copper, which means it's the best conductor. Okay, so in terms of applying your knowledge, why is the handle wood? Why is the saucepan actually metal? Remember, we need the heat to get through the metal to heat the food, so the metal needs to be a good conductor. The handle needs to be an insulator. Which bench would feel warmer to sit on? This is a little bit more complicated, the wooden bench or the metal bench. And if you ever sat on metal benches, they do feel very cold on a cold day, whereas a wooden bench might not feel as cold. And the interesting thing is that both of these benches would be at the same temperature. If they are outside on a cold day, they're both going to be around 0 degrees or 1 degrees if it's a freezing day. So they're both the same temperature, but the wood feels warmer because it's a worse conductor. So the heat, to be frank, in your bum stays in your bum and doesn't conduct into the wood. Whereas when you sit on the metal, the heat in your bum conducts into the metal, so the metal in effect takes heat away from your bum, so your bottom feels cold. Okay, so just to apply our knowledge, we need to link it to real world. What's this person doing? Why are they doing it? You may have had this done in your house. This is when you have cavity wall insulation or the insulation between walls, and we're going to think about why you might do this. Or you could have a question here. You've got a wooden house or some kind of a metal house or a glass house. Which would keep the heat in the best? Would it be the wood or the metal or the glass? And this is going to link to our ideas of conduction. So this is a required practical, and AQA call it the thermal conductivity of paper. We have got another video in this in more detail, but I'm just going to quickly talk through the general idea of it. If we accept that heat will flow through the walls of a house by conduction, if a material is better at conducting the heat, then we say it has a higher thermal conductivity, just like the table. So what we could do, we could test this. We could test, does a thicker wall transfer heat energy at a slower rate than a thin one? Now, to do this, we'd have to come up with an experiment, and the suggested experiment in the lab at school, you've probably done something like this. You've taken 3 containers that are the same, and you wrap one in 10 layers of newspaper, one in 20 and one in 30. We pour the same amount of boiling water into the 3 different containers, so our control variable is the same amount of water. We put a lid on the container to keep as much heat in as possible from evaporation, and we put a thermometer in the water. We wait until the temperature reading stops going up on the thermometer, and we record the starting temperature, and we start the top watch, and then we record the temperature every minute for 10 minutes. And this is quite a straightforward practical, but again, you need to remember how to do this. Remember the safety. The kettle shouldn't be carried around. Move your beakers to the kettles. We've got a very simple diagram. You'll be able to draw your own results table that you've definitely done in the lab, where you're showing for each number of layers of newspaper what the starting temperature was, and also how it drops every minute. Okay, so in terms of conclusions for this, hopefully you would find that the thicker the newspaper, the better it was at keeping the water. So in terms of the thermal conductivity, we need to think about what this means. So heat energy passes through the walls by conduction. We know that. The rate that the heat passes through the wall definitely depends on the thermal conductivity of the material. This is what you're wrapping it up in. It also depends on the thickness of the material. From your experiment, you would have found the thicker the better. And it would also depend on the temperature difference. And this idea is that if you're trying to keep something that's very hot, that's harder than keeping something that's fairly hot. So the hotter the water was, the more rapidly the temperature of the water will drop. But the general idea from this practical is that the lower the thermal conductivity of the wall, the less heat energy passes through it. So this is a case of lower is better if you want to keep your house warm. So going back to our picture of the houses, you'd have to research whether or not glass, wood or metal has got the lowest conductivity, and you would want to choose something with a low conductivity, and that would keep the heat inside of your house. So just a little note on the end of this, it is a required practical. So make sure that either from watching this video or our other video on the site, you've got a good idea that you can write a suitable method and explain what you did and how the results help you prove your hypothesis.